I'm happy that Annabelle and Ingrid agreed to give Beyond the Classroom series here on polymer properties. I know many of us have been in this room and seen stress strain curves or rheology data, and maybe that's something I'm not familiar with on a kind of day-to-day basis. And again, I think one of the goals of these Beyond the Classroom series is to introduce you to kind of the fundamentals of what these kind of data mean and how to interpret them. You probably won't be an expert after this presentation, but I hope that some of the language that's used in this presentation and in subsequent research presentations will be a little bit more familiar. And of course, Annabelle and Ingrid and others in the center who work in these areas are happy to, I think, meet with you and talk with you about more detailed aspects. So I'm going to turn it over. I don't know who's first, actually, but one of the two folks, Ingrid, who's co-advised with Frank Bates, or Annabelle, who is advised by me, to start the presentation. Please, go ahead.
Hi, I'm Annabelle. And I'm Ingrid. And today we're going to talk to you about Polymer Properties 101. But before we start, we're going to start with a brief safety moment. And this is where we're going to ask you to consider having a pair of lab shoes that you keep on campus. Having them be lab appropriate, closed-toed, non-slip, and supportive. And this makes it so that you can wear other shoes into lab. You can preserve your nice, expensive shoes for other days when you're not in lab. And you can also prevent wearing warm winter boots all day by having an extra pair of labs in your office. With that, we're going to start our presentation on Polymer Properties 101.
So first, to go over an outline of what we're going to talk about today, we're going to split this up into 3 sections. In the first section, we're going to talk about glassy materials. And we've put here as high TG. We're going to first define what these properties that depend on temperature are. Then we're going to go over what a stress strain curve means and how it relates to mechanical properties. And then we're going to review some common plastics that everybody should be familiar with and how the tensile properties define those. In the second section, we're going to look at rubbery materials and how their properties are dependent on time, and then look at some strategies of how to make these materials actually applicable to everyday use, and how those rubbery materials that we know and use a lot relate to mechanical properties. In the third section, we're going to combine these glassy and rubbery polymers and talk about some efforts that we're doing in the CSP to make thermoplastic elastomers. So first, we want to talk about 2 types of polymers that everyday plastics consist of. And so the first one is a thermoplastic. This is when you have bulk polymer that are just polymer chains that have not been chemically reprocessed. So these can be heated up and remolded and processed several times to get multiple uses out of them. There are also thermosets where you have, again, polymer chains, but these have been chemically cross-linked to enhance their character, but when you heat them up, they burn rather than being reprocessed, so they're typically one-use materials. We also want to talk about the glass transition a lot today. So the glass transition is when the polymer goes from a solid glassy-like material where polymer chains are frozen into place that cannot move into a liquid-like material where the chains are now flowing past each other and we actually see more liquid behavior. To actually quantify what this means, we can talk about it in terms of free space arguments. So you see here on the right, at really high temperatures, the relative space that polymer chains have to move around in is really large, and so the polymer chains can move really easily and they can slide past each other. As we see going to the left, the temperature decreases. The relative volume that these polymer chains have to move is steadily decreasing until we get to the glass transition temperature. And at this point, there is not enough space for these polymer chains to move, and now they are frozen in place. And we want to emphasize here, they're frozen into an amorphous state. They're not ordering, and here that's why we have an amorphous polymer. There are other thermal characteristics that we want to be aware of, and importantly here is crystallinity. Due to entropic reasons, the entire polymer chain cannot line up and order itself, so we call it semi-crystallinity, where we have domains that can be small, where the polymer chains overlap for that small segment. So here, what we can see is at low temperatures, we have a glassy material where it's below its TG. When you heat it up above its TG, instead of becoming liquid-like, it retains its solid character because these crystalline domains are able to keep the polymer solid. And so then when we heat the material above its melting point, we get into the true liquid regime. We also want to emphasize that only some polymers can have a melting point, but all polymers have the glass transition.
So in the first part of the talk today, we're going to talk to you about materials that have a high glass transition temperature. This means that at room temperature, they're going to be solid. And so we're going to take polystyrene as an example. We might be familiar with how polystyrene is used in everyday materials, such as the CD case shown here. Polystyrene has a glass transition temperature of 100 degrees. And so if we take polystyrene, and we can get polystyrene either as pellets from its native source, or we can get it from recycled materials, we can put it in a hot press and melt and bring the material above its glass transition temperature. We can then press the material, and it will flow, and it will fill the space of the mold. We can then cool it back down, and this is how we can reprocess thermoplastics. We might we might use everyday words to say how a CD case behaves. We might say it's strong because we're obviously using it to protect a more fragile CD case, and it does a really good job at preventing damage to the CD. We might also call it rigid because it's not very flexible. It doesn't really bend when you try to bend it. And then we might call it brittle because if you bend it a little too far, it'll snap in half rather than give way. So what we want to do is we use these words every day. However, we want to test the material, quantify those properties, and associate these results back to these words we use. So to do this, we do a tensile test. We make a thin film of this material using compression molding like we showed previously, and we cut out these little dog bone shapes. We take each end of the dog bone and we pull it, and we can measure the strain, which is the displacement over the initial area, the initial length, as a percentage. We can also measure the stress, which is the force we apply per unit area. This results in this very simple stress-strain curve, where the point at which it breaks is denoted by the X. This gives us two values, the ultimate tensile strength and the elongation at break. We also see that in this linear regime at very low strain, we can get this is deemed the elastic regime, where if you stretch the material, it'll for very low strain, it will come back to its original shape. In this regime, we can get the elastic modulus, which is a measure of the stiffness of the material. So not all materials break in this way, and so something else that can happen is we might stretch it into its elastic regime. And if we release the stress, it'll go back. But if we extend it further, it might yield, and it might plastically deform, and then it might break. And so a stress-strain curve will look a little more like this. Where at low strains, we're seeing that elastic deformation again, and we can see take the elastic modulus in this regime. We'll also pass through the yield point where it starts to permanently deform, and this is called the plastic deformation region. And then we can see the material breaks at much higher elongation at break, denoted by the X again. And the area under the curve is denoted as the toughness. So now how do we take all of these quantities that we can get from a stress-strain curve and in a tensile test back to our everyday words we use? Well, if we have, depending on where the ultimate tensile strength is, we can say the material is either strong or weak, depending on whether it has a high ultimate tensile strength or a low ultimate tensile strength. If we can only stretch it a little bit before it breaks, we might deem the material brittle. If we can elongate it much further and significantly further, then we can say the material is ductile. The elastic modulus, which is the slope in the elastic regime, gives us how rigid or flexible the material is. And then we might get a tough material when the material is both strong and ductile. One thing that we don't get from a stress-strain curve or in a tensile test is the ability to call a material hard or soft. Hardness is measured more using an indentation test and not through a tensile test. And so we're going to try our best not to use the words hard or soft for the rest of this talk. And then these the stress strain curves on the right just show 3 typical types of behaviors you may see where when a material breaks at low strain and high stress, it's strong, brittle, and rigid. When you get high stress and high strain at break, you'll see a tough material. And when you see that the material elongates really far but breaks without that much force applied, it's a weak and flexible material.
To go back to our example of polystyrene, we all know what a CD case feels like. And so to look at this tensile test, you can see that we have high elongation, or we have high stress at break, which means that this is a strong material. It takes a lot of force to break it. However, we have really low strain at break, which means that you don't have to deform it that much before it's going to break, so this is a brittle material. Also, the slope of this line is very steep, so this is called stiff. So we would deem this polymer to be brittle, strong, and stiff. In the next couple slides, we're also going to talk about several other plastics we should be familiar with, and we're going to talk about the tensile properties as well. We want to point out that all of these plots are on the same axis so that you can directly compare the values of these polymers. So polylactide is probably the most common renewable material that we talk about here and that is available. And so we typically use this as something that we want to replace polystyrene with. You can see that this is pretty this is a good replacement because it has a lot of the same properties. It's also brittle, strong, and stiff. It has approximately the same stress at break, and it has a little bit higher strain at break. This is also a stiff material, and so that's why we use this as a replacement for polystyrene. You see that this also has a high TG above room temperature, and it also has some crystallinity, which can impart some of these other behaviors. Another example that we all know, and you might even have some with you today, is water bottles, which are made out of polyethylene terephthalate. This has a similar glass transition temperature to polylactide, and it has a much higher melting temperature. You can see that this polymer breaks at much higher strain, and so it's no longer called brittle. Instead, there is more area under the curve, so we can call this material tough instead. This still breaks at relatively high stress, so it's strong, and again, the slope of the line is very steep, so it is stiff. To talk about another kind of material, we also want to look at epoxy resins. So these are actually cross-linked materials with high TGs. So it is solid-like because it has high TG, but it's also cross-linked, which introduces more solid-like character. Because it has more solid-like character, we can see that we have more extreme properties in all of these. We have more stress at break, less strain at break, and an even steeper slope. So this is a case of a more extreme, strong, brittle, and stiff material. So in this first section, we've talked about materials that are solid at room temperature, and they can have a lot of functions that you can, like they can hold water or in CD cases. And they have properties that are tough, strong, stiff, and brittle. So at this point, we would like to stop and take questions about the first section.
So in this section of our talk, we're going to transition into low glass transition materials. And what we mean by this is where the glass transition sits below room temperature. So if a polymer has a low glass transition temperature, you would expect that at room temperature it would be a liquid. And these polymers are used in lubricants and in other liquid products, and they're also used as additives. Not only are we interested in studying this liquid behavior because the polymer acts as a liquid at room temperature, but when we're processing these materials and we're heating these materials above their glass transition temperature, they also act liquid-like and flow over time. So we want to be able to understand what's happening when these materials are being heated. And so one of the interesting things about polymers is that they are viscoelastic. They exhibit both solid and liquid-like behavior. And silly putty, as some of you may have with you, is a very classic example of viscoelastic behavior. At low temperature or short time frames, the material will behave solid-like. So if you roll your silly putty up into a ball and you bounce it on the table, it acts like a solid, it bounces. At high temperature or over long periods of time, the silly putty will behave liquid-like. So if you leave it on the table and walk away, you'll end up, the material will deform to the shape of the table or whatever it's on. And so this is a very classic example of viscoelastic behavior. Now we can touch it, silly putty, play with silly putty, and see this behavior, but how do we quantify that? And we can use rheology. We load up a polymer, and just like in a tensile test, we apply a strain deformation and measure the stress response. In this case, the strain deformation is applied in an oscillatory manner, and so there's a frequency involved with the strain, and then we measure the stress response, and this gives us the modulus. So if we look at the modulus as a function of temperature or frequency, we can see that at low temperature or high frequency, we get a high modulus. This is the glassy regime, and you get solid-like behavior. At high temperature or very low frequency, we get the modulus slowly decreases, and so you get liquid-like behavior, or in the terminal flow regime. The interesting thing about polymers, actually, is that there's another regime where the material also behaves as a solid, albeit with a lower modulus or a lower stiffness. And this is actually due to entanglements between the polymer chains. These entanglements act as physical crosslinks, so when we're doing rheological measurement, we can probe these physical crosslinks in the polymer. So if we take a low glass transition material and we covalently crosslink it, we give it solid-like property. But the thing is that it doesn't actually feel like a hard or a rigid material when it's as if it is below its glass transition temperature. What happens is if you look at the modulus for the cross-linked red material above the glass transition temperature, you can see that the modulus plateaus and actually never flows again. It doesn't decrease over time or at higher temperature until it actually starts degrading. So in this cross-linked material, it behaves solid-like, and you can also obtain this with semicrystallinity. You can have this solid-like behavior where the modulus plateaus at a slightly lower modulus than the glassy regime. And then once you hit the melting temperature, it might begin to show liquid-like property again.
So to give an example of this, we can talk about linear polyisoprene. You see that it has very low TG, almost 100 degrees C below room temperature, and so this is very liquid-like at room temperature. I'm going to point out that this plot is plotted against the frequency, and so it's inverted from what we saw before. If we look at very high frequency, this is where we have glassy behavior. We could see that we can say the modulus is about 10 to the 9 because it plateaus and we can read what the modulus is. Then as we go to lower frequency, we hit the rubbery plateau again. From here, we can see that while it will still act like solid, it does have a much lower modulus, here about 10 to the 6 pascals. We can also calculate the entanglement molar mass from this value if we wanted to. And finally, at the lowest frequency regime here, we can see that we have a steady decrease in the modulus, which is really indicative of the liquid-like behavior. We can also look at polyisoprene if we were to introduce chemical crosslinks. This is most readily seen in rubber bands. So we all know rubber bands are really stretchy and that you can pull them apart and they'll come back. This is typically made with disulfide bonds with polyisoprene, where the polymer chains in between the crosslinks are really long. So this means that as we pull it apart, the polymer chains are able to be pulled apart much farther, and so we get a very high strain at break. This makes it very flexible, but because we don't have that many crosslinks in the system, there's not that much solid behavior imparted onto the polyisoprene, and instead we get a weak material. Another example of something that's typically cross-linked is polybutadiene. This is what tires are made out of, and it also has a disulfide bond to do the crosslinks, but here the polymer chains are relatively short between the crosslinks. This means that when we try to pull them apart, the polymer chains can't go along the same way as the polyisoprene chains can, and so instead we get a much lower strain at break. However, because we have more crosslinks in the system, we have more solid-like behavior, and so we have a stronger material. This also has more area under the curve, so we also call this a very tough material. We don't need to introduce chemical crosslinks in order to get this kind of solid material, and so like Annabelle was talking about in the question and answer section, polyethylene does exhibit solid-like behavior. It has very low TG, below 100, minus 100 degrees C, but it also has a very high melting temperature. So at room temperature, it will be rubbery because it's above its glass transition temperature, but these physical crosslinks of the semi-crystalline domains keep the polymer from flowing like the poly or like the silly putty would do, and instead we get solid materials. So you can have two different types of materials, high-density polyethylene and low-density polyethylene. These are typically different percent crystallinities, where high-density polyethylene has much higher crystallinity. This makes like milk jugs or laundry detergent bottles where you touch them, they're stiff, they're stiffer, and they take a lot of force in order to deform them. Also with high-density polyethylene, there is a very steep curve, and you see that there's more area under the curve for this, so this is a tougher material. Low-density polyethylene has less crystallinity, and so it's a lot weaker and it doesn't have the same toughness. This is typically what plastic bags are made of, and so you can see that it's much easier to rip those bags apart because it doesn't have the same mechanical properties. So in this section, we've talked about low TG materials and how we get those kinds of properties. Well, we can still get the same strong, tough properties that we got with high TG materials. We can get new properties such as plastic behavior, elastic behavior, rubbery, and just plain liquid. So at this point, we'd like to stop again and ask if you guys have questions about these types of materials. Okay, so in the third section, we want to talk about some efforts that we're doing in the CSB to make elastomers that behave like classic thermosets. So thermosets are like rubber bands and tires, like we talked about in the last section, where they have really good properties, but if you were to heat them up, rather than flowing and being reprocessed, they will just burn. These are made by cross-linking the materials, and they can be recycled. We typically do this by actually chopping up the materials and then recombining them into different products, and this is called downgrading materials. So they don't have the same mechanical properties, and they don't have the same, it's just not the same, and we would like to be able to actually do the traditional heat recycling process. We can do this using block polymers, where we have a polymer of chemistry A covalently linked to a polymer of chemistry B, and then in our example have a third block where we link it back to the same polymer of the same chemistry A. What this does is the materials that do different chemistries don't want to mix, and instead they phase segregate into domains that are rich of the first polymer and other domains which are rich of the second polymer. By having different compositions, we can get different morphologies, which can be important to a lot of different applications, but here it can give different mechanical properties. So typically what we do is we use materials that are glassy, so materials that are below their glass transition temperatures, and a mid-block material that is above its glass transition temperature. This means that we can combine the properties that are both glassy and rubbery, because those domains that are rich in polymer A are going to exhibit solid-like behavior and give that kind of character to the rubbery mid-block domain. This can be compared to like vulcanized rubber materials, and we can show you that we get some pretty similar properties. These are actually shown to be really relevant in industry as well. Typically people use polystyrene, polybutadiene, and these are sadly not sustainable materials, but you can see this being used in kraton and like asphalt. Also the bottom of rubber shoes like sneakers are made out of black polymers, as well as some adhesives.
So cratons exhibit, the styrenic-based polymers from kraton exhibit very great properties. And so we're looking at researching sustainable alternatives to these thermoplastic elastomers that we see in our everyday lives. By looking at polyesters, we get polyester linkages along the backbone, allowing degradability. And in the case of our high TG end block, or our glassy end block, we're looking at using polylactide, which is ubiquitous for its renewability. For this polylactide end block, in this blue square here, we can either use an amorphous polymer, which only exhibits a glass transition temperature of 60 degrees, or we can use a semi-crystalline polymer, which has the glass transition as well as the melting temperature. For the rubbery mid-block, we've chosen polymethyl caprolactone as it has a low glass transition temperature. It will still be rubbery at the cold temperatures we see here in Minnesota as well as over at Cornell. So once we have this block polymer and we have this thermoplastic elastomer, how do we test it? We can use compression molding, as we showed you back in the polystyrene slides. Or in the lab, we can solvent cast the material. We can dissolve the polymer in a solvent, put it in a petri dish, let the solvent slowly evaporate, and obtain a film. We can then cut multiple tensile bars out of this film, and we want to reproduce this tensile test multiple times. Not only can we do tensile testing, but we can also do rheology on a tensile bar on a solid material. And so instead of oscillating the strain rotationally, we can oscillate the strain uniaxially, so with a tensile bar. And so for this tri-block polymer system, you can see that at really low temperatures, below the glass transition temperature of both polymers, you get the glassy behavior where the modulus is high on a scale of 10 to the 9 pascals. As we heat the material, the modulus decreases and we get that solid-like behavior again. And this is where we get that rubbery, elastomeric behavior for these block polymers. Then for the black curve, where we have amorphous PLA-N blocks, the modulus slowly decreases as the temperature increases above the glass transition temperature of the PLA. So it becomes more liquid-like as we heat it above the glass transition temperature. We can get a higher operating temperature for these materials if we use semicrystalline PLA because it has a higher melting temperature, and then we can extend this rubbery plateau region up to higher temperatures by selecting a different block. If we look at the stress strain curve for this material, for this block polymer, we can see that we get really high elongations at break, about 1,000% strain. This means we can stretch it 10 times its original length before it breaks. We also get high stress at break, and we can get even higher stress at break when we use semicrystalline PLA. In both of these materials, because they can elongate far and they break with high force, we also can say that they're tough. With block polymers, not only can we look at elastomeric rubbery materials, we can look at a wide variety of properties by changing the composition of how much glassy material we impart and how much rubbery material we impart. So if you can see, if we have a higher fraction of polylactide in this block polymer system, we can't elongate the material as far in the orange curve, but we get a much higher stress at break. And as you can see, if you look in the very, very low strain region, there's a steep curve for that 40% PLA material, and this is where the material will yield, and it is stiff, so you can feel the stiffness of the material before it yields. You can also get really weak and high elongation at break materials by incorporating only a little bit of polylactide, but then it's still solid enough for us to be able to process a film from it and do a tensile test so it doesn't flow at room temperature. So by using these block polymers where we can incorporate both glassy and rubbery components, we can get really versatile materials and we can change how these materials behave. We can also combine a wide variety of polymers. So we can choose, a wide variety of polymers for the rubbery component and select a wide variety of polymers for the glassy component, and pairing those two, we can get a lot of different types of materials. And because they are not chemically cross-linked, they're only physically cross-linked. If you bring it above the melting or glass transition of the highest thermal transition that exists in the polymer system, you can process and remold these materials. So with that, we hope we've shown you a little bit We've given you more versatile vocabulary for using, for describing polymers, and we've given you an insight onto polymer properties. We'd like to thank the Center for Sustainable Polymers for the opportunity to give this talk, and we would be happy to take any questions.